All right. Welcome, everyone. So today we'll move on now and start talking more about enthalpy of reactions. Okay. We'll probably just mainly go over that stuff today. And then Monday and Wednesday next week, we'll be talking about kind of changes in internal energy, talking more about state functions and such, and using kind of some mathematical definitions of what a state function is to eventually get to the relationship between constant pressure and constant volume heat capacity in general for any type of gas, ideal or non-ideal. Okay. And for those lectures, I will highlight some of the certain things, but I'm not going to go through and do some of the derivations that will be on the lecture videos that will be posted. Yeah, there will be a number of kind of derivations where we will manipulate partial derivatives and define some things and blah, 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 blah. And they won't do a lot of that kind of mathematical hoopla in class here. And we'll just kind of, again, hammer home some of the main points. But yeah, and then the exam will be a week from Monday. It will cover everything that we'll get to and including Wednesday. So basically, I think that's topics 1 through 11 in the syllabus. Okay, and after that, we'll be talking about entropy. Any questions people have before we get going here? I do have the homeworks graded. I'll hand them back for those who are here. I'll keep them with me for future days of class for those who are attending virtually and have a hard copy they'd like to get back. If you submitted your homeworks online, I don't really have a hard copy for you, but I will post the grades. I enter the grades on my computer. I haven't uploaded those to Canvas yet. I'll do that after class so you can check it out. For one or two people who submitted their homeworks online, I'll just make a note that there wasn't the full homework submitted, and I don't know if that was just a issue of not all files got added to like the PDF that was uploaded or something like that, or maybe you didn't have time to finish it. I don't know, but just keep in mind, like, when you see your score, especially those who submitted it online, if it seems extremely low, it might be because I only had a couple of problems of yours to grade. And if you believe you did more than those few problems, contact me and we can figure out what went wrong. And, and I'll happily grade whatever missing problems there were. Okay. All right. Got questions? Yep. Yeah, up to topic 11, I believe. I can pull out the, let me pull out the syllabus real quick. relation of CP to CV. Yeah. So. Yeah. So I'll upload one more video for next week, and I'll probably upload a video for the review of just like going over equations to know and to not know and things like that. Well, yeah. So I'll upload 2 more videos. I'll get those posted soon, tomorrow, for next week for kind of Wednesday and Friday. Yeah. Other questions? All right. So, right, we've started talking about enthalpy before. We mentioned, right, that enthalpy is a state function. We mentioned, right, that for the expansion or compression of a gas, our enthalpy change is related with our heat capacity and our constant pressure, right, change in temperature, right. For a chemical reaction, you can relate enthalpy and internal energy, right, with that you know, already, right. And today we're going to talk a little bit more about enthalpies of chemical reactions. How can we get the enthalpy of a given chemical reaction, calculate that, understand it, and then we'll also talk about the temperature change of enthalpy with chemical reaction. All right. So as a review of these things, right, what is like a standard state? So often we'll talk about the standard enthalpy changes for chemical reactions and things like that. And so when we're referring to that, what do we mean with saying something's in its standard state? What's that saying about, say, a gas? I have a gas in its standard state. Yeah, 1 bar. So yeah, so an element in its most stable form at a given temperature, right? If it's a gas, it's 1 bar for standard state. I'm trying to remember the other one, right? There's like standard state and something else that like literally the only difference is 1 bar versus 1 atmosphere. The normal, I think it's like when talking about your standard boiling point is your boiling point at 1 bar, and your normal boiling point is your boiling point at like 1 atmosphere, some stupid thing like that. But specifically, standard states refer to 1 bar, right? So gas, pressure of 1 bar, right? Your element is in its most stable form, okay, at whatever given temperature is, right? There's no standard state temperature, it's just whatever temperature, right? And what about for, say, something dissolved in a solution? 1 molar concentration, right? And liquids and solids are in their pure states, okay? So that's describing something at its standard state. Now specifically, gases being at 1 bar will come back when we talk a little bit later in this semester about chemical equilibrium and other things like that. And we'll talk about essentially the molar Gibbs energy. I can think of the symbol that describes it, but I can't think of the name of it. Anyways, right, we'll get to it later in the semester. Chemical potential. That's talk about chemical potential and things like that. Standard states and other stuff will pop back up again. But yeah. All right. And hopefully you've kind of seen some of this stuff before in other chemistry, general chemistry, and things like that, right? I believe in 1341 they talk about Hess's law. I don't know if people remember that. Maybe I'm wrong. They talk about it. I actually haven't taught 1341 here, so I don't know. I taught 1342, but maybe actually I talked about Hess's law in there. I don't know. Anyways, anyone know or can remember what Hess's laws were related to? Yeah, enthalpy change and yeah, right. So Hess's law, right? What that's getting at is, right, is that I can, if I have a set of reactions, go here, right? Let's say I have, right, reaction A plus B going to C, and then C plus B going to E, plus F, and E plus G going to H plus I or something like that, right? Like whatever, like some set of reactions, right? When I sum these up, my total reaction is like A plus B plus D plus G going to cancel, so F H9. Right? I mean, then I didn't want to have to think of a whatever reaction, right? But I have these reactions, right? And I have to find delta H1, delta H2, delta H3, and then the enthalpy for this reaction I'll call delta H total, right? Right, Hess's law is just basically saying, right, the total enthalpy change, right, I can get from this enthalpy change of 1 plus delta H2 plus delta H3, right? And on the electrolytes, this is kind of drawn as sort of the idea. You start here in state 1, your final state 4, right? My total reaction is going from 1 to 4, but here in my mechanism, I'm going to kind of zoom this out, right? Manual zoom here, right? In my mechanism, right, I have kind of these intermediate states 2, 3 that I go through, right, in order to get to 4, right? And it's just saying, right, that the enthalpy change here, right, is just this. This is enthalpy total, and this delta H1, delta H2, delta H3, right? That my total enthalpy change, right, is just the sum of those 3 enthalpy changes, right? And why does this work for enthalpy? Why can I do this for the enthalpy of a reaction? State function, right? It's a state function, so that's why the enthalpy change from 1 to 4 is the same as going from 1 to 2, 2 to 3, 3 to 4, because in the end, I go from 1 to 4, right? It doesn't matter if I went directly from 1 to 4 or if I went indirectly through some circular route from 1 to 4, right? In the end, all I care about is what's my initial state, what's my final state, right? Because enthalpy is a state function, right? And so kind of Hess's law, if you will, works the same for internal energy, for enthalpy, or yeah, enthalpy, obviously, Gibbs free energy, entropy, okay, right? All of these state functions, right, have, you know, their own Hess's law, if you will, right? Like I can sum up the Gibbs free energy, the enthalpy or entropy or internal energy of a bunch of chemical reactions to get the total value, right, if I want to. And it's purely just because these things are state functions, they're path independent. So they just care about what are the reactants and what are the products, right? Not what's the intermediates, what's my mechanism. Okay. Right. And so what is the standard enthalpy of formation referring to? Or what is a standard like formation reaction? Is another way I can ask that. Right, let's say I want to know what is the standard formation reaction for NH3 gas, right? NH3 and its right, its standard state is a gas. Okay, so what is the standard formation reaction for NH3? Right, so yeah, so right, the name, it's a formation reaction, right? So the reaction should be forming NH3, okay? And then what should I be putting as my coefficients for this reaction? Balance it. Yeah, so one NH3, so in a formation reaction, your product always has to have a stoichiometric coefficient of 1. So in which case, right, this has to be 1/2, and this has to be 3/2. Okay. So yeah, normally you'd balance it by putting like a 2 in front of NH3 and then a 3 in front of H2, right? But for a standard formation reaction, you need to have just a stoichiometric coefficient of 1 in front of your product, okay? and then the product is being formed from its elements in their standard states at whatever given temperature you're talking about here, right? So for example, NH3, right? Nitrogen in its standard state is a diatomic gas. Hydrogen in its standard state is a diatomic gas at room temperature, right? And so that is the enthalpy, right? That is the standard formation reaction for NH3, and the enthalpy for this reaction is defined as the enthalpy of formation, right, for NH3, okay? And this is technically like a molar, okay? This is like a molar value, molar enthalpy of formation. So this will be something like kilojoules per mole, okay? So enthalpy of formation reactions, and typically standard enthalpy changes and things like that are often molar values, and we just don't really say molar blah 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 out of laziness. Okay? Not just me, like it's other places as well. They just put enthalpy formation and things like that, and it's a molar value. So just keep that in mind. That often these enthalpy changes for reactions, right, are given in per mole quantities. Okay, even if they aren't called molar enthalpy changes directly. Okay? Right. And so the enthalpy of formation of some substance is just what is the enthalpy change for that enthalpy formation reaction, right? And so what would be the enthalpy of formation? So what would be enthalpy of formation of, let's say, Cl2 gas? 0, right? That's because, right, the formation reaction, if we were to write that, would literally be just Cl2 gas. Oops, 2 there. Going to Cl2 gas, right? No reaction, nothing going on, so there's no enthalpy change, right? So enthalpy of formation, right, of an element in its standard state is 0, okay? Because again, enthalpy, as we talked about when we first talked about enthalpy, we briefly mentioned, right, that there is no absolute value for enthalpy. There is no like predefined absolute value of enthalpy. So when we talk about enthalpies of a substance, of NH3, of O2, of Cl2, right? When we're talking about the enthalpy of these things, we don't actually talk about what is the enthalpy of O2, right? Instead, we define these enthalpy of formations, which are just the enthalpy changes for a given reaction, where the reaction is what we define as these formation reactions. Okay, so when we talk about entropy, right, we don't have these like entropy of formation reactions. You just have like the entropy of a substance, because entropy, like internal energy, has a defined value, has an absolute 0, right? And so we can do that. But for enthalpy, there is no sort of predefined value, nothing that says what is the inherent enthalpy of NH3, right? There is no inherent enthalpy of NH3, but instead we can talk about the enthalpy of formation of NH3, okay? And that is what we think of as sort of the inherent enthalpy of NH3, is its enthalpy of formation, okay? And so that's why, again, for elements in their standard state, those enthalpy of formations will be 0, because the formation reaction is not really a reaction at all. Questions about this stuff? All right. And right, given the idea behind Hess's law of essentially delta H as a state function, right, and these enthalpy formation reactions, I can write the enthalpy, the standard enthalpy of any reaction as a sum of the enthalpy of formations of the products minus the sum of the enthalpy of formations of the reactants multiplied by their stoichiometric coefficients. Okay, so VI here is the stoichiometric coefficients in the balanced chemical reaction. Okay, right? I mean, because and this equation is literally just saying, like, right? The idea is take the enthalpy of your products minus the enthalpy of your reactants, right? Enthalpy of your final state minus the enthalpy of your initial state gives you the enthalpy change, right? That's all this equation is saying, right? Enthalpy change of your reaction is the final state, which are your products, minus the initial state, which are your reactants, okay? It's just, again, for enthalpy, we talk about enthalpy of formations because there's no predefined value of enthalpy, okay? right? We'll see this same exact equation pop up for entropy, for example. And in entropy, there isn't an entropy of formation. It's literally the entropy of a substance times its stoichiometric coefficient, right? To give you the total entropy of that thing, right? And again, we're just going to do your final entropy minus your initial, final enthalpy minus initial, right? To get the enthalpy change for the reaction. So questions about this equation here?
What is the R subscript?
R is for saying for a reaction. So the standard enthalpy change, so that the superscript 0 here is implying standard state. So often the superscript of 0, okay, the enthalpy is implying standard state values. And then R here is just saying for a given chemical reaction. And then F is indicating for specifically for a formation reaction, right, of that substance. Okay. And the subscripts I are indicating like you're summing over all your different reactants or products. And things like that. Other questions? Right. So for example, right, if I had the chemical reaction O2 plus 2CO going to 2CO2, right, my standard enthalpy change of that reaction would be 2 times the enthalpy of formation of the product, because it's stoichiometric coefficient of 2, minus 1 times enthalpy of formation of O2, minus 2 times enthalpy of formation of CO. Okay. Again, those factors of 2 and 1 come from the balanced chemical reaction.
So that the coefficients is the way that product.
Well, so get the product in 1 mole. So for regular chemical reactions, the stoichiometric coefficients doesn't matter. Now, we'll talk just a second about what happens when you change those stoichiometric coefficients, the enthalpy of that reaction, right? But the reason why, oh, I forgot I don't have that on the slide, right? But the reason why the enthalpy of formation reactions have to have a stoichiometric coefficient of 1 for the product is for this kind of formula to work, right? If these enthalpy of formation reactions formed more than 1 mole, if you will, of your product, you then have to divide by that, right, in order to right, you need to make sure, right, because essentially what we're doing, let's write out that, 2 here, CO, okay. All right, essentially what's going on is, right, in this reaction, O2 plus 2CO going to 2CO2. Okay. Oh, I didn't actually share that screen. Right, so that's my chemical reaction. O2 plus 2CO plus CO2, right? I'm going to create this reaction from the following reactions. I'm going to create it from the O2 going to O2 kind of enthalpy of formation reaction, right? O2, which happens to be 0, right? I'm then going to have the C solid plus 1/2 O2, oops, O2 gas going to CO gas, right? And then C solid plus O2 gas going to CO2 gas, right? And this is the enthalpy formation reaction of CO, right? And the enthalpy formation reaction, circles there, right, of CO2, right? And these equal some value that whatever they are, right? And so, right, so if I gave you this problem here, right, you'd kind of look at it and say, okay, this is like an application of Hess's law, right? I get to manipulate my chemical reactions to get the final enthalpy change of my overall reaction, right? Which, so now we'll talk about what happens, right? So if I, right here, I mean, again, the O2 one's kind of redundant because whatever, it's not really a reaction, but I wrote it just for the sake of completeness, right? Let's focus on CO, right? So here, in this reaction, CO is a product. I want CO as a reactant. So I got to flip, right, my reaction here, which means that I need delta F formation of CO, the minus sign, right? So if I flip my chemical reaction, right, that means the enthalpy gets multiplied by -1, right? And then I want 2 CO here, and because these enthalpy formations are defined specifically to have just a stoichiometric coefficient of 1 in the products, I know that then I need to be multiplying my enthalpy formation of CO by 2 in order to get stoichiometric coefficient of 2 here, right? If the definition of this reaction had like a 2 here, then I wouldn't be multiplying this by anything. But then I got to remember enthalpy formation of this has a coefficient of 2, and that has a coefficient of 5, and that, you know, like, so that's why we just say all enthalpy formations, the product, there's just one product, and that one product has a stoichiometric coefficient of 1. Okay? And so, and so that's for CO, right? Technically, I have like minus enthalpy of formation of O2 here, right? Again, well, I don't know, you don't have to flip through. It's 0, so whatever, right? But for the sake of kind of what we were doing, right, you'd put a minus because, yeah, O2, and this detailed example is kind of annoying because the reaction isn't really a reaction. But anyways, and then finally we have CO2, right, which is in the products. So we just add it, right? We don't flip it, so it's just going to be added, right? Right, but then I have to multiply by 2 because there's a stoichiometric coefficient of 2 here, right? And so that gives me this equation, right, which is the exact same thing as if, right, we start off with the equation of delta H of the reaction, right, the sum of the coefficients, the enthalpy of formation of the products, right, minus sum IBI, the formation of the reactants. Right? I use this formula, it gives me the exact same thing here. Right? So this formula is literally just, right, constructing any chemical reaction from enthalpy of formation reactions using Hess's law, right? Using the fact that enthalpy is a state function, right? That's where this formula comes from. Okay. Right. And so, right, so in the example here, right, right, the enthalpy change of this reaction, right, is sort of an enthalpy change like per mole, if you want to think of it as like a per mole thing, like of a specific quantity, it would be something like per mole of O2, right? Because it's, right, for this reaction, how it's written with these stoichiometric coefficients, right, it's 1 mole of O2 gets used up, gives me some enthalpy change for that reaction, right? But if I wanted to express the enthalpy change of this chemical reaction in terms of per mole of, say, CO2, I would have to divide it by 2, right? Because it is stoichiometric of 2 in front of you. So just kind of keep that in mind, right? That based off of what your stoichiometric coefficients are in your chemical reaction, and you know what kind of the per mole is kind of related with the enthalpy change of that reaction, right? Because like, let's say I'm given, I burned up, you know, or like that I consumed 5 moles of CO for this chemical reaction here at the bottom of the slide, right? And I had the enthalpy change of the reaction was 10 kilojoules per mole. I wouldn't just do 10 kilojoules per mole times 5 because I have this stoichiometric coefficient of 2 here, right? So the 5 moles that's being burnt up, right? It should be 5 halves times 10, or more specifically, I guess 5 moles times 10 divided by 2. Maybe I could write all this stuff out verbally, right? Use the same paper here, right? Let's say, right, the enthalpy change for this reaction as written is minus 10 kilojoules per mole, right? That per mole is like this idea of like per like mole of thing, like transfer, per mole of like reactant transferring. It's not necessarily per mole of CO, okay? Because CO has a stoichiometric coefficient of 2, right? When this reaction goes forward, 1 mole worth of stuff, right? It's really 1 mole of O2 kind of going forward because of the stoichiometric coefficient of 1 here, right? And that means 2 moles of CO is being consumed, right? And such, right? And so if I wanted the enthalpy change, right, for, burning 5 moles of CO, okay, enthalpy change would equal 5 times enthalpy change of this reaction divided by the stoichiometric coefficient of CO here too, okay, which would give me 5 times 10 over 2, negative 10 over 2, which would give me negative 25 kilojoules per mole. Or not per mole, just negative 25 kilojoules, right? So I burnt up 5 moles of CO. Okay. Questions about that? So again, just keep that in mind, right? That enthalpy change for a given chemical reaction, right, when it's a per mole quantity, isn't necessarily per mole of the thing you care about, right? It depends kind of on the stoichiometric coefficients in that chemical reaction. All right. So given the enthalpy change for this following reaction, what is the enthalpy change for the production of 2 moles of CO? Yeah. B? Is that what you said? So right, so if I'm given the enthalpy changes plus 131 kilojoules per mole, and we have a balanced chemical reaction, forms 1 mole of CO for every mole of reaction that takes place, if you will. And so I'm burning up 2 moles, or producing 2 moles of CO, right? And I want 2 times the enthalpy change of the reaction, give me plus 262 kilojoules. So A here. Questions? Right. Just a reminder of these changes, right? What is the enthalpy change for this reaction? Yeah, so Danielle and everyone here, right? A, right? I flip the reaction, I get a minus of the initial enthalpy change. So A here, minus 131 kilojoules. All right, so we can calculate what the enthalpy change is for this reaction, carbon graphite and carbon diamond, given the 2 following enthalpy of reactions. So number of people saying C here, right? Right, and so to get the answer right, we got to flip the diamond reaction because diamond needs to be a product. So we flip reaction number 2, which means it's a positive 396, and then I add those 2 enthalpies together, and the difference between those is going to be a positive 2 kilojoules per mole. So it's going to give us C here, positive 2 kilojoules per mole, right? Which is true. I don't know if it's exactly 2 kilojoules or not, but it is true that graphite is actually a more like, the enthalpy of graphite is lower than that of or no, I shouldn't say lower. Let me rephrase this. Right, that the final enthalpy change for this reaction, saying that it's uphill to form diamond from graphite, is true. That technically, first reaction, diamond going to graphite, is exothermic, right? Releases energy. You get to a more stable form of carbon in graphite than you do in diamond. Okay. Now, obviously, that reaction doesn't take place on any sort of time scale because kinetically it is very awful and slow, right? And that's just kind of a random reminder that, right, what we talk about in this class in terms of enthalpies of reactions and eventually Gibbs free energies and spontaneity and things of that nature, right? Just because some reaction is spontaneous, just because spontaneously diamond should from graphite doesn't mean it occurs in any time scale of the universe, right? Right. So spontaneity does not mean kinetically fast. Okay, just as a reminder, right? In this class, we're not talking about kinetics. We're not talking about how quick something happens, right? Just that naturally it will occur. It will occur, right? Right. Given enough time or given enough input energy, if you will, to overcome whatever reaction barrier or things like that that you might have. Okay? Right. All right. All right. We kind of talked about this before, right? Hess's law works because of what? It's a state function, right? It's a state function, right? Intensive, extensive has no does not matter. And then being a path function is the exact opposite of what you want. Right, and so I can apply the principles of Hess's law to which of these three things? Yeah, change in internal energy, right? Because only the change in internal energy is a state function, right, out of these three things. The principles behind Hess's law can be applied to internal energy, just like it can entropy and Gibbs free energy. Okay? Which of these reactions is essentially an enthalpy of formation reaction, where the enthalpy change for these reactions is equal to the enthalpy of formation for the given product. What was that? D? Not quite. So one thing I guess we forgot to mention is that for an enthalpy of formation reaction, right, or a formation reaction, I should say, right, for a formation reaction, there must be only one product, because you have to be forming just one thing. So yeah, so D can't be it because there are multiple products.
It has to be pure elements.
And it has to be what now?
Pure elements.
Yeah, and the reactants also have to be pure elements in their standard states. That is also why. So C, as written, doesn't quite work because C is not balanced. B, diamond, is not actually the stable form of it, so it's going to be E, Na solid plus 1/2 Cl, NaCl salt. Okay? Right? Salt is a solid at room temperature. Right? Okay. So in this one, it's E. So A is not the case because the stoichiometric coefficient of 2 in front of H2O. E is not just because graphite is actually the more stable form of carbon. Okay. Right. So at standard temperature, 1 atmospheric pressure conditions, carbon would form graphite, not diamond. Okay. C is not the case just because it's not balanced. Not a balanced chemical reaction, right? D is not the case because your reactants have to be pure elements and you have to have just one product. And then E works because it satisfies all those things.
So C was N2 plus 2O2.
And then it would be fine. Yeah, yeah. So that one is kind of, a little trickier because it's like, oh, well, I'll just balance it and then it'll be fine, right? So I guess I should have written like as written, right? Which of these things work, right? All right. All right. So Kirchhoff's law, the temperature dependence of enthalpy of a reaction. Okay. So online it is kind of the derivation of this, right? But it basically comes from how enthalpy itself depends on temperature, right? And then using that dependence of enthalpy on temperature and then kind of rearranging some equations, things like that, you get kind of this relationship. Oh, I forgot to delete the previous slide thing, right? It's not on the previous slide. In the derivation, it was on the previous slide, but I deleted that, right? But anyways, right, delta H here is saying what is the change in enthalpy of a reaction with temperature. Okay, so how does the enthalpy of my reaction change with temperature, right? So that's why there's like this delta H, right? Delta H is just like the enthalpy change of a reaction, and then this extra delta on the outside is kind of indicating how's that changed with temperature. Okay. And this is related with the integral of what's called delta Cp here. We'll talk about what that is in a second. dt, right? So delta Cp, right, is the heat capacities at constant pressure, okay, for your products minus times your stoichiometric coefficients minus the molar heat capacities, I should say, of the reactants times their stoichiometric coefficient, right? So this familiar form, right? We've seen this. I'll go back to that in just one second, right? This exact same form as the enthalpy of a reaction here, right, is the same for this delta Cp for a given reaction here. Okay? And if delta Cp is temperature independent, right, this integral just comes out to give you delta T, right? So then delta H is equal to delta Cp times delta T. Okay. Right. And again, so delta Cp is the change in heat capacity when going from reactants to products. Okay. Right, and that's what that's referring to, is how is your heat capacity at constant pressure changing when going from reactants to products. Okay. Right. And assuming delta Cp is independent of temperature is a very good assumption. Because while Cp itself might not be constant with temperature, the temperature change in the heat capacity of a given reactant and the temperature change of the heat capacity of a given product are going to be relatively similar, so that when you take the difference between those two, that difference in heat capacities is pretty much temperature independent. Okay? And so while Cp itself might not be that temperature independent, delta Cp is fairly temperature independent. And we never deal with delta Cp not being temperature independent. Okay. Right. I don't know what extreme case you got to get to where this doesn't work for a chemical reaction. Okay. But all right. So questions about Kirchhoff's law here. Delta H equaling delta Cp times delta T. All right. So given the following heat capacities, molar heat capacities at constant pressure, calculate delta Cp for the formation reaction of 1 mole of H2O gas. We got A's here, right? Yeah, I think I might have typed mine in wrong or something. Yeah. I got something very, very close to that. Yeah, yeah. That's why I have negative 9.95, right? But A is fine, or if you decide to say E because it's not quite the same thing, that's fine as well. But yeah, roughly 8, right? Negative 9.95. Yeah, is what it is. Okay. All right, but we get essentially A, right, negative 9.95. You get that by doing, right, the product heat capacity, right, 33.58 minus 28.84 minus 1/2 times 29.37, right? Because the enthalpy, right, the formation reaction, right, of H2O is H2 plus 1/2 O2 forming H2O, right? And so you need to multiply the O2 by half and add that to H2 and then subtract that from H2O. And that gives you 9.9 something, okay, or negative 9.9. All right. So for the reaction here, delta H is 23.1 kilojoules at 298 Kelvin. But delta H is equal to 19.7 kilojoules at 373 Kelvin. If CPM for the product is 27.3 joules per Kelvin mole, what is CPM for the reactant? No, not B. Sorry. Huh? So let's look at how we solve this. Right? So, right, this is looking at an enthalpy change in enthalpy with a change in temperature for a reaction. So we're going to be using that Kirchhoff's law, delta delta H equals delta Cp delta T. We're given delta delta H and delta T effectively, and so we just need to find kind of delta Cp using this, right? So delta delta H, I'm going to call this my final temperature, the 19.7, and my initial temperature, 23.1. So it's going to be 19.7 minus 23.1 is my change in enthalpy with change in temperature, right? Some delta Cp. That corresponds to a change in temperature of 373 minus 298. Okay. So when I divide this over and simplify, I will get delta Cp is equal to minus 45.3. Okay. This is joules per Kelvin. Okay. So to get that right, you have to multiply this thing by 1,000. Okay, because this difference divided by this will be 75 here, right? So this difference divided by this is going to give us kilojoules per Kelvin, while the CPs that are given in the problem are in joules per Kelvin. And so we need to multiply it by 1,000, okay? Make sure it's joules per Kelvin, because the CP that's given, right, delta Cp is the CP of the product, right, which is given of 27.3 joules per Kelvin, right? The stoichiometric coefficients were 1 and 1, so I multiplied it by this 1 to get rid of the mole, right? Then minus the CPM of the reactant that I'm looking for, right? And so I just need to add this onto the other side, right? And I get CPM of the reactant is equal to 27.3 plus 45.3, okay? Which that comes out to be 72.63 D. So yeah, so for this one, it's one of these ones. And when, again, we just need to remember, and a lot of times we have certain things that are given in joules and other things that are given in kilojoules, right? Entropy is one of those examples. It's often joules per Kelvin, just like heat capacities. And so, especially when we start talking more about entropy, a lot of times we'll have things that are in joules and other things that are in kilojoules, and you just got to make sure you're keeping track of what's joules, what's kilojoules, and that they're all the same, right? That you either convert all your kilojoules to joules or all your joules to kilojoules to make sure everything has the same units, so you can add and subtract them appropriately. Okay. All right. Other questions? Or any questions, I guess. All right. Another quick one here. So delta H of reaction is minus 51.3 kilojoules at 301 Kelvin. What is delta H of the same reaction at 371 Kelvin if delta Cp of the reaction is a positive 32.6 joules per Kelvin mole? so what equation do I need to use to solve this? Right, then.
The same one, delta H.
Yeah, the Kirchhoff's law, right? That delta H equals delta Cp times delta T. Okay. Now in this problem, right, we're given what delta Cp is, and we're given delta T, and essentially we're needing to find what that change in enthalpy is, right? So delta T is just 70 Kelvin, right? 371 minus 301 is 70 Kelvin. Delta Cp is 32.6, right, joules per mole. So take that 70 Kelvin times it by 32.6, and that will give me that's something in joules. I need to divide that by 1,000 to get 2 kilojoules. And when you do that, you'll get around 2.2 kilojoules, I think it is. Yeah. And so delta Cp times delta T is around 2.2 kilojoules. And that equals the enthalpy that we're looking for at 371 minus the enthalpy at 301. Okay. And so that's going to be minus a negative. So this will be, so you have to subtract that over to the other side. And so really what you have is you have like negative 51.3 kilojoules plus 2.2 kilojoules, right? Get a final value of 49 kilojoules here. Okay. Oh, yes, all of these should be negative. Shoot. That's a mistake on my part. I should have had all of these be negative. Yeah. It should be a negative 49 kilojoules. So yeah, so it'd be none of these because all of these are positive, and so it doesn't really work. That's my mistake, right? And we should expect the value of the enthalpy to get less negative or more positive because delta Cp is a positive number, right? A positive change in heat capacity means that with an increase in temperature, you're increasing your enthalpy, okay? Becoming more and more positive or less and less negative. Okay? Right? Yeah, so if there was a minus sign here, it would be negative 49 kilojoules. Okay. It would be if there's a negative. Okay. All right. So standard enthalpy of formation for gaseous water is 298 Kelvin. At 298 Kelvin is minus 241.82 kilojoules per mole. What is its value at 392 Kelvin, given the following molar heat capacity? All right, to do this problem, right, we have some problem where we're trying to get the enthalpy of formation at a given temperature, okay? And what we're dealing with is a case where we have some chemical reaction that we're looking at a different temperature than the initial value, okay? We're given the enthalpy at that initial value and the molar heat capacities, the constant pressure, the reactants, products. So we should be using this Kirchhoff's law to solve for this problem, right? So the first thing we need to do, right, we have Kirchhoff's law, enthalpy at 392 minus enthalpy of 298. Okay. We can add the enthalpy of 298 over if we want, right? And we have to solve for delta Cp, which is Cp of water, minus the Cp of H2, minus 1/2 the Cp of O2, right? And then we need to multiply that by our temperature change. Okay. And so when you do that, you'll get this minus 934 joules, and compare that then with the enthalpy at 298 Kelvin of minus 241 kilojoules, right? We first got to divide this by 1,000 to get it to kilojoules, and then add them together to get minus 242.76 kilojoules. Okay. Questions? All right. So here, it's just a Hess's law problem, right? Calculate delta H for this chemical reaction given the following chemical reaction. I think this one I'll just you guys can kind of go over it. The answers are posted on the slides already on Canvas, right? But essentially, right, it's just how do I manipulate these reactions to get this reaction here, right? For these problems, the best thing to look at is to look at like the things you're interested in, right? Boron here, right? I'm looking for B solid, right? Where do I find B solid? Okay, here, it's in reactants, so that's good, okay? It has this coefficient of 2, great, right? Here, I'm looking at, I like to look at things that are more unique, like B2H6 and B over H2, right? B2H6, right? We want it in the gas phase, right? And the products, right? Well, here I have it as the reactant, so I'm going to flip this reaction. But this reaction involves B2O3, which is a solid. And so luckily it looks like it cancels that reaction, so that's great. But then I got some water floating around O2, so I need to use these reactions to get rid of them, right? So there's sort of this trickle-down effect with some of these things where I suggest starting with like the more unique things, not like hydrogen gas, oxygen gas, and things like that. Things like B solid, B2H6, and make sure those match up with the reactions you're given to the reaction you want, and then use kind of the rest of your stuff to kind of get rid of, like, say, the oxygens that you're not wanting and waters you're not wanting and things like that. And when you do that, kind of in that way, then things will cancel out in the end. So anyway, so yeah, so you can kind of test yourself on that. I'd rather us kind of talk about, the time we have left here, how we get the enthalpy, right, and the internal energy change for this chemical reaction. Okay. Right, so if I want the enthalpy change for this reaction, the enthalpy of formations, right, what would I be doing? What would I need to do to get the enthalpy change for this reaction? Well, so the reaction itself, right, so the C2H5OH, right, that is the reaction we're looking for, its enthalpy change for that given reaction. And we're just given the enthalpy of formations of some of the reactants and products in that reaction. So how do I relate the enthalpy of the reaction with the enthalpy of formations? Right, yeah, so it's going to be the enthalpy of formations of the products multiplied by their stoichiometric coefficients minus the enthalpy of formations of the reactants multiplied by their stoichiometric coefficients, right? So I'd have, 2 times the enthalpy of formation of CO2 plus 3 times the enthalpy of formation of water minus the enthalpy of formation of C2H5OH, right? And then oxygen, right, its enthalpy of formation is 0, so you don't need to worry about including that, right? So we do that to get then the enthalpy change for that reaction, right? And then how would I get the internal energy change for this chemical reaction? what equation do I need to use that relates enthalpy and internal energy for a chemical reaction? Yep. Yeah. It's RT delta NG. Yep. So we need to use this relationship between delta H and delta U. When I have some chemical reaction where the number of gas moles change, right? Here, right, I have 2 gases in the products, 3 in the reactants. So my delta NG is -1. Temperature is 298, right? So my H is what we calculated previously, right? Solve for delta U, and then you plug in these things and convert from joules to kilojoules here. Okay. You'll add that over to get delta U is fairly similar, right? The difference between delta U and delta H is about 2.5 kilojoules, right? Not a big difference here. Okay. And that's often the case. A lot of times for enthalpies and internal energy changes for reactions, they're fairly close to each other. They are a little different, but typically it's 10 or less kilojoules difference between enthalpy and internal energy changes for a given chemical reaction. All right. The last one here, I have 100 milliliters of water, given its density, it's boiled at 100 degrees Celsius, converted to gas, or H2O gas, right? At 1 atmosphere pressure. And the question is, what is delta H, delta U, W, and Q for this process when the enthalpy of vaporization for water itself at 100 degrees Celsius or 398 Kelvin? No, that's not true. That should be 373 Kelvin. I only put 398. 125 kilojoules per mole. That's the wrong temperature. It should be 100 degrees Celsius converted to Kelvin there. Let me fix that real quick. That's not like a trick in the problem. That's a typo on my part. 373 Kelvin, not 390. So let's talk about how we would get these things, right? How would I try to get the enthalpy change for this phase change, right? Essentially what's going on in this problem is I have a phase change. I'm going from a liquid to a gas. So how would I get the enthalpy change for that phase change? What is the total enthalpy change for vaporizing 100 milliliters of water? How would I calculate that total enthalpy change? Yep, exactly, right? I'm given the enthalpy change for vaporization per mole, and so I just need to figure out how many moles I got, right? And so the number of moles I have is converting, right, 100 milliliters to moles, right? Use the density, convert from milliliters to grams, right? And then you use the molar mass, convert from grams to moles, okay? So you just convert that 100 milliliters over to moles of water, and you can then use that to get the enthalpy change. How would I calculate the internal energy change for this phase change? Yep. So, right, the enthalpy change, or the internal energy change is delta H equaling delta U minus RT delta NG. Okay. Right? That relationship. Now, technically, since you're given the volume of the water, you could technically do this by doing like, instead of minus RT delta NG, you could do minus P external, which is 1 atmosphere, times the change in volume to get the change in volume by ideal gas law, and then, the initial volume of 100 milliliters. But what you'll find with the ideal gas law is that the volume of the gas is much, much, much greater than 100 milliliters. And so that volume of the gas minus 100 milliliters is basically the volume of the gas. So yeah, that would be, yeah, that would then kind of, that P delta V would then also give you W if you did it that way. But yeah, so that's right how we would get work, right? You're expanding against a constant external pressure, 1 atmosphere, so it's just minus P external delta V, right? And then again, the volume of your gas, you can get the ideal gas law. The volume of the liquid is given. And then Q, we would get by 1. Yeah, so you can get it from delta U minus W, but it actually ends up being just delta H for this problem, right? Because this is a constant pressure expansion under mechanical equilibrium, right? The pressure of your gas and the external pressure are the same. They're 1 atmosphere, right? As you're forming the gas, as you're boiling it, the gas is being formed with 1 atmosphere worth of pressure, okay? Right? It's just as you're forming more moles of your gas, the gas is taking up more and more volume, right? 1 atmosphere worth of pressure of vapor, right, and water vapor, right, when it's initially being formed, it's just not taking up much volume what's initially being formed versus as it's getting formed later, right? Okay. So yeah. So, right, so you get delta H by finding moles, it's around 5.5 moles, okay? Delta U, again, you can use this equation, right? Right here, I had to divide by 1,000 to convert to kilojoules, right? Again, the volume, you see the final volume of that 5.5 moles of water, right, is 181.26 liters, right? So the delta V is 181.16, right? I promise you that this number will be almost the same, right, with 181.2 versus 181.1, right? Right? There really is not much of a difference, okay? And then, right, you should see here Q is should be the same, 694. Oh, okay, so I did something wrong with the calculation somewhere here because delta H and Q should basically equal each other. Well, wait, did I just multiply that by 0.1? This gives me 10. Is that off by 10? No, 3. I'm trying to decide if maybe because here, right, when I calculated work, I used the volume of my liquid. When I calculated like this term here, I ignored the volume of the liquid. Okay. And so, but still, oh, it's because I used the wrong temperature here. Okay, there we go. That, yeah. So problem. I did this. That's why. Okay. Yeah. Q should come out to be what delta H is. I just have the wrong temperature here. So my calculation of delta U is incorrect. Okay. All right. So questions about this problem? I know for some of these last problems, I didn't give you a lot of time to kind of do it yourself, but you know, at least hopefully us kind of talking through how to do it together kind of help. And then again, you can always go through and work on these problems by yourself on your own time as well. They're all posted on Canvas as well as with the answers, which are mainly correct except for some of these, like this one here, where delta U is not the right number. So, all right. So for those who want their homeworks that are here, you can come up and grab it. Make a couple of front here. Like I said, I will bring the homeworks with me for those who are here on Zoom and who do come to class, but just didn't come in today. I will bring the homeworks with me for a couple of days, but you can always grab them at my office as well whenever you'd like. Okay. So any questions from those with us virtually here before I close this Zoom session?
Did you say you did bring them if we submitted them online?
No, if you submit them online, I don't have a hard copy.
Okay.
I will have the grades right after class. I'm going to go back to my office and put the grades on Canvas. The grades will be on Canvas within 10, 15 minutes. So you can check them out there. But again, if you submitted something online or emailed me them, just double check your grade to make sure that,
It looks right.
yeah, that it looks reasonable, right? Like, you know, if it's not 100%, don't be like, it should be 100, you know, but there's a couple of people where I only had like 2 problems from them or something like that. You know what I mean? And so I don't know if that was just they didn't have time to do all the problems, or when they uploaded it, it didn't upload everything that they meant to upload. So,
Okay.
yeah.
Cool. Appreciate it.
Yep. All right. All right. We'll close out the Zoom session here. Doesn't seem to be any questions. See you guys on Monday.